Now we're going to learn about elliptic cones. So this is an example of the graph of an elliptic cone, and as you can see, it's really similar to a hyperboloid of one sheet. However, this point where the two sheets supposedly intersect is only a point, and it's not like a hyperbola like that. It's only a point. So this is the difference between an elliptic cone and a hyperboloid of one sheet. This is the equation, and as you can see, the right side is 0 instead of 1. So the right side is always equal to 0 if it's in this format, and we have 3 degree 2 terms. And so we have 3 degree 2 terms, 2 of which are positive, or they have positive coefficients, so we have a plus sign, a coefficient of +1, and we also have one negative coefficient here. So basically the negative coefficient is so this z here is in the negative coefficient variable, right? So our graph is parallel to the z-axis. So basically now let's just try to graph an elliptic cone to get the feel of this. So let's try this equation: x squared over 9 plus y squared over 4 equals, or you can say minus z squared over 16 is equal to 0. So we're going to use traces, and if you don't remember, traces are like, we're going to graph what our graph looks like when it intersects different planes. So before the graphing, I'm going to explain a little bit about why this equation produces an elliptic cone, because that's an interesting theory. So basically, if I let z be 0, I get a point, right? And if I let z be any other value, so if this term here is -1, then if I move this to the other side, we get this thing's equal to 1, okay? So this is an ellipse, and so this is an ellipse, something like that. And as my z increases, I get like a larger and larger ellipse, etc. So yeah, that's just the theory. So basically that's just why it produces an elliptic cone. So now let's just graph the x, y, and x, z, and y, z traces. So our first trace is the x, y trace. So I have the x-axis and y-axis, and if I just let the z term be 0, then basically what I have is, x squared over 9 plus y squared over 4 is equal to 0. That's not exactly helpful because the only values for x and y to meet this equation, so x squared over 9 plus y squared over 4 is equal to 0, is when both values are 0, so basically a point. That actually makes sense because you see this here, this is actually a point. However, that's not exactly a helpful trace because it's really easy to graph a point. So that's not really helpful to graphing our graph. So how about we make an ellipse? So we let z be 4, and we have x squared over 9 plus y squared over 4 equals 1, because when z is 4, this term here is minus 16 over 16, which is just minus 1. If we move minus 1 onto the other side, it's just plus 1. So now we have an ellipse, and we can easily graph that. So we have major focuses and also the minor focuses. Like something like this. So that's our ellipse, and then basically we graph the xz trace. So this is our xz trace, and when we graph the xz trace, we let y be 0. So if we have the y term as be 0, we have x squared over 9 equals z squared over 16. So y is 0, right? And then we can move this term onto the right-hand side. And basically, this is just a set of lines, so there are 2 lines here. So why is that? So if you just take the square root of both sides, you have x. So you have plus minus x over 3 equals z over 4, right? And then if you just move 4, if you just multiply both sides by 4, you have plus minus 4 over 3x. So these are two lines. One is z equals 4 over 3x, one is z equals minus 4 over 3x. So we can graph that. So let me just move this up here. So we just move this equation up here, and basically if you just graph those lines, we get something. So they both intersect at the origin, and that also makes sense. But okay, so we need another point. So say I had 1, then one point would be somewhere here, one point would be somewhere here. So our lines would look something like this, and they intersect at the origin. So I'll put some arrows to indicate that they keep going on. And this actually makes sense because see, so the xz plane is over here, right? So actually, if the graph is actually close enough to intersect the plane, you actually get two lines, something like that, because that's just how elliptic cones intersect. So now let's graph the yz plane. So we have the z coordinate and the y coordinate, and then basically in this case we let x be 0, so we get another set of two lines. So we have x squared, so no, x is 0, so we have y squared over 4 is equal to z squared over 16. If we just take the square root of both sides, we have z squared, so we have z over 4 is equal to plus minus y over 2. So plus minus y over 2. And then if we just multiply both sides by 4, we have z equals plus minus y over 2 times 4. So that just gives us plus minus 2y. So basically, so if we just verify that, so basically let's just try that again. If we have, so we just take the square root of both sides, we have y over 2, plus minus y over 2 is z over 4, and then we multiply both sides by 4. Yeah, we have z equals 2y, plus minus 2y. So the two lines are approximately something like this. They intersect the origin. So I'll add some arrows to indicate that they go on forever. So basically those are our three traces. And if I just zoom out for you, so now we can graph the whole elliptical cone. We have the z, so we're going to draw the 3D coordinate system now. This is z, this is y, and so this is z, this is y, this is x. And firstly you can graph the ellipse, so the ellipse would look something like that. So let me just use a different color. Something like that. And then we have the lines, and the lines intersect at the origin, so probably something like that. So I'm not going to graph that because it's for the side view, and we're looking from the front view. So for the z and y, we have something approximately like that. And the bottom is also an ellipse. So this is like our approximate graph. Let me just make that ellipse better. So this is our approximate graph, and we can actually just color this in. So these are all part of our graph. However, just remember that the inside of our cone isn't, only the outside. So this is also the outside of our cone on the other side of it. So the inside of our cone actually doesn't count as part of the graph. The points inside the cone don't match our equation. So if we plug those into our equation, they don't work. So this is our, well, you can say elliptic cone. So thanks for watching. Bye.